Morning, Chem students. We're looking at lesson 3.3 today. My voice is a little bit rough, so if it cuts out, my apologies. But here we go. So I can use evidence from investigations to propose a battery design that results in the largest energy output. So remember, you are an engineer or scientist in the city of Chicago. So your interest is making vehicles that will actually work for the city, right? We want to meet Chicago's energy needs while minimizing environmental impact. Also knowing that what we're talking about for this lesson is where's the energy coming from and what are some trade-offs when we use batteries to power vehicles. So again, if we're making a battery for an electric vehicle, it has to have a high amount of energy output. So that's what we're looking at today. Excuse me. Specifically, we are going to look at the investigation that you did with the electrodes and the voltmeter to make some sense of it. We're going to look at the role of electrolytes in solution, so that water, salt, and vinegar, and then update our initial models. When you're done today, and I'm going to underline this for you, this thing, that battery design proposal, please do that on Google Forms. So here we go. You can pause the video if you need to. Make sure that you have your scientist notebook set up. It's clipped in your binder so you don't lose it. And we're going to specifically be taking notes on sense making and then electrolytes. So once you have all that, keep moving. So let's identify some evidence from our investigation to help us to determine which metals would make the best battery. Write these answers in your scientist notebook, please. So what matter? Again, that substance, that combination of metals provides the highest amount of energy per electron, which is voltage, that moves in the system. That to say, which electrodes gave you the most voltage? From what I saw in most classes, Al and Cu were the ones that gave you the highest when those two were in the beaker together. That gave you the highest voltage. Any thoughts though on what happened at station 1? That's where we just had aluminum and aluminum. What happened there? Because what you should have seen is that the voltage read 0, 0, 0, or if you had the really accurate one, it might have said like 0.006 millivolts. We're talking like super low voltage. Why? Why was it so low? Well, the reason is because they're the exact same type of metal, okay? So if we have the exact same type of metal, if it isn't metal A and metal B, I erased it. If it isn't metal A and metal B in your model, it's not going to actually produce electricity. So remember, or think about rather, that even though electrons in solid metals are not strongly held to one nucleus, they kind of move around in that sea of electrons. Some metal nuclei, center of an atom, exert stronger attractive forces on these electrons than other metal nuclei. We're going to make sense of this. But what are some of the things we know about the structure of an atom that would influence how strongly it attracts electrons? So maybe you talked about this thing, the nucleus, and how there's those positive protons in here. And you know that the negative electrons, just like a magnet, positive, negative, they'll attract each other. Or maybe you talked about how if there's a whole bunch of these rings of atoms, the one on the very outside is kind of shielded by these inside ones. Remember that from our electron unit test. Maybe it's shielded, okay? So there's some of the things that influence how much this nuclei wants to pull that electron towards itself, okay? Again, think magnets, positive, negative. So if we remind ourselves that electronegativity is the ability of an atom to attract electrons, it's basically like how much it wants an electron or how much it can pull on an electron. It's going to help us make sense of why there is more voltage for certain electrodes. So if we look here, remember electronegativity increases as we go up and to the right. So these ones over here, fluorine is the highest electronegativity. But we're going to look right here at the metals we just did in this investigation. So we have aluminum, Zn zinc, Cu copper, Fe iron, okay? So this is what we're looking at here, and these numbers represent just how much they want to pull an electron. Oh, it's going to leave me behind if I do that. Hold on. Let's keep my floating head moving here. So consider electronegativity. How do I make this go away? Hopefully you can't see that random little bar. Consider electronegativity in our results and write your answers to the questions below, again, in your scientist notebook. So why are electrons not pulled towards one of the metals in station 1? Again, that was just aluminum. Aluminum and aluminum. So aluminum and aluminum. Why were they not pulled? This one's electronegativity is 1.61. This one's is 1.61. Yeah, I mean, they're exactly the same. Nobody's pulling more. They have the exact same number. Let's think about some of these other ones. Which metal is pulling more on the electrons and why? So if we set up here Al and Cu, Cu is 1.90, which is copper. Aluminum is 1.61. Which one do you think is going to pull more? Okay, now why? Exactly, because of the fact that this has a higher electronegativity, it really wants that electron more, so it's going to pull the electrons in this direction, which will increase the voltage. The bigger the difference, the higher the voltage we're going to get out. This last question here, what stations transfer the most energy? I guess I just kind of did that for you, but as a recap, the ones with the biggest electronegativity difference. So biggest electronegativity difference. And if we think about forces, the pull or push, it's because there is a pull for the electrons. Kind of like if there's a tug of war, pull for electrons. Just going to write here, tug of war. If you imagine aluminum and copper getting up here, the one that's strongest, copper is going to pull that electron more towards itself. Okay, great. So we've been talking about metals and batteries, but why do we need that solution of electrolytes? Why is that necessary? What could we change about the electrolyte to make the battery transfer more energy and therefore improve our battery design? Pause here, turn and talk to somebody next to you about this. Get your mind thinking. All right, I'll try to move this along. We're already at 7 minutes. So make sure you have this definition in your scientist notebook under the electrolytes heading. Electrolytes, again, is when we have a salt that's added to water, it breaks into ions, and ions are atoms with positive and negative charges. So if we take table salt, NaCl, it'll break into Na plus and Cl minus, okay? So because they have those charges, they'll be attracted to the opposites, much like a magnet. So Na is going to get attracted to negative things. Cl, since it's negative, will get attracted to positive things. So the flow of electrons from the anode to the cathode this way leads to a buildup of negative charge. So we keep getting these negative electrons coming in here. So we're going to get a negative charge happening over here. And this is going to prevent the electrons from flowing forever, like it would stop flowing. So we need these electrolytes to kind of cancel out the charge buildup from the electrons flowing in the wire. So what's going to happen is our electrolytes that are floating around in here, they are going to be used to cancel out this buildup of negative charge over here. Because this thing, the anode, is losing electrons, losing negative things, so it's becoming more positive. This is becoming more negative, and as a result, it's going to build up charge, and we need to cancel that. So pause here, think about it. Which direction are the positive ions, the Na plus, going to move? Which way are the negative ones going to move? If this is a overall negative charge, and this is over an overall positive charge, which way are they going to move? Okay, now take your fingers, put them to the screen, and do this with me. So left finger is on the positive ions, the Na plus, right pointer finger is on the Cl minus, and we're going to move kind of opposite as it were. So my right pointer finger is in blue, it's holding this, it's going to move towards that positive end. In green, my left pointer finger is going to move towards the negative. Okay, so they're just going to move like a magnet. They're going to move towards the direction of where the charge is. All right, so let's think about the role of electrolytes in batteries. Again, write these answers in your scientist notebook. So how might increasing the amount of electrolytes affect the current? Reminder that current is how quick the rate of the charge moving. What do you think it'll do? How would it affect it if we have a lot more ions in there? Then overall, how would that affect the energy in the battery? Okay, so looking here, we have a few different electrolyte solutions that we could use to create a battery. We have calcium chloride, magnesium sulfate, potassium chloride, sodium chloride. That's table salt. That's what we've been talking about mostly so far. And it shows you the current. This is in mega amps. Don't worry right now about what mega amps are, but you can see there's a trend moving up, okay? Higher the mega amps, the faster the current. So which one would you want to use to create a battery with the highest energy output, and why? Hopefully, it's kind of clear that the one you'd want to choose is the one with the highest output, the highest current, because that means it's going to be able to move that electricity quickly. We want high voltage because that's a high amount of energy, and then we want high current because it's going to move it quickly. Yeah, reminder that current is how quickly, the energy can move through. All right, last thing here, update your model with the realizations. You have this model hopefully already in your binder. You're going to update it. Make sure that you add to it that you have these ions, positive ions moving this direction, your negative ions moving this direction, and that's because that flow of electrons across our battery. And then just kind of put this on the side. The metal B is going to pull more strongly on the electrons in the wire than metal A, which is going to make the electrons move. That's that electronegativity. It really wants those electrons. As the cathode gains electrons, it gets more and more and more of these electrons. It's going to get that negative charge because it's collecting all these electrons. So those positive ions are going to pull towards it. And then as the anode loses electrons, it's going to get more of a positive charge, which is going to pull those negatively charged ions towards it. And all that in the desire to stay neutral. Now, if we run out of electrolyte solution, that's when our battery no longer can move power and our battery doesn't work anymore. So that's why a AA battery, for example, you can't recharge it. Most likely, it's just going to die after a while because the electrolyte solution is spent. Okay, take all this with you. Go do the battery design proposal. It's a Google form. You're going to need to cite information from in here. I want you to really talk about the matter, so the metals, the electrolytes, talk about the energy movement, the electrons, and then talk about forces that push and pull. Reminder, that's kind of what we're putting together here, and that's our thinking. We have the matter, the energy, the forces, and they all interact with each other in our MEF triangle.